Okay, hello everyone and welcome. It's great to have you with us today. Um, the title of my talk is The Cosmic Perspective, which is essentially having a sense of who we are in relationship with the rest of the universe and with deep space and deep time, and allowing that understanding to influence our thoughts, our behaviors, our perspectives, and mindsets. So what I'd like to do is take you on a journey to space, explore some of the mysteries of what's out there, and then come back to Earth and try and make sense of what we've learned. I suppose a good place to start is to ask ourselves, where does space begin? The international space boundary is set at 100 kilometers above the Earth's surface, around 62 miles above the Earth's surface. And the reason for that is, above 100 kilometers, the atmosphere becomes too thin for aeronautical flight. Planes, for instance, couldn't fly that high because there isn't enough air. So the international space boundary is set at 100 kilometers above Earth. The next question is, how far is it to the moon? The moon is on average around 380,000 kilometers from Earth. The Apollo 11 astronauts were traveling at 3,000 kilometers an hour for 3 whole days non-stop until they reached the moon. Now, the Apollo 11 astronauts weren't the first astronauts to reach the moon. Apollo 8 and Apollo 10 missions also reached the moon, but they didn't land on the surface. They circumnavigated the moon in orbit. And astronaut Will Anders took this amazing picture of Earth. And what's surprising about this image is, for the first time, we see Earth up in the night sky. And the beautiful blue of Earth is juxtaposed against the dull, lifeless gray of the moon's surface. And there in the background is the hostile blackness of outer space. As a quick aside, there's a lot of conspiracy theorists out there that say we didn't land on the moon. The fact is, we absolutely landed on the moon. There is no shadow of a doubt that we did. And I believe we landed on the moon not because NASA says we did, but because the Soviets and the Chinese say we did. At the time, the Soviets and the Chinese were keeping a very close eye on the mission. And if you look at Chinese and Russian textbooks, even today, they absolutely acknowledge that Neil Armstrong was the first man to land on the moon. And we have many other pieces of evidence about it, but suffice to say, we did land on the moon. This image is called the Blue Marble. It was taken by Apollo 17 astronauts in 1972, and it's called the Blue Marble because this is one of the first images of Earth without any shadow. You see the full face of the Earth. There's Africa and Madagascar to the right, and Antarctica all down below. And this was taken 45,000 kilometers from Earth. And in this image, the sun is behind the photographer. So you have the full face of the Earth. And this was a very important image. It had a huge impact on our collective human psyche. It had a huge impact on the global environmental movement and the global deep ecology movement as well. So it had a cultural impact on human society. I'd now like to move to a quick description of Voyager 1. As many of you know, Voyager 1 was a space probe launched in 1977, and its mission was to take images of Jupiter and Saturn and some of the outer gas giants. And that's what it did. You know, we launched the Voyager 1 probe. It used the gravity of Mars to slingshot itself towards Jupiter, took astonishing images of Jupiter and its moons, of Saturn and its rings, and then its mission was over, and it was all set to drift off into deep space. But it was the genius of Carl Sagan who asked the mission control commanders at Houston to turn the cameras of Voyager around and take a picture of Earth from 6 billion kilometers away. Most people were wondering why, because you wouldn't even be able to see Earth. But they still took that image, and when we processed the image, we discovered the image had 500,000 pixels of mostly nothing, because space is vast and empty. But Earth did feature in that image. Out of the 500,000 pixels, Earth was half a pixel. And that image was famously known as the pale blue dot. And I'm sure most of you have heard Carl Sagan's response to this beautiful image. But if you haven't, then I urge you to go back to the default world, get on YouTube and type Carl Sagan pale blue dot and listen to his monologue. It is one of the most profound and sublimely beautiful pieces of response of scientific literature in response to this image. Voyager 1 is still out there, and on board is a golden record. And I want to share a quick anecdote about something that happened here in Black Rock City in 2017. Back in 2017, Black Rock Observatory was placed out in deep playa at 11 o'clock, halfway to the trash fence. And nearby the observatory, someone had built an installation of the golden record. And the golden record was placed aboard Voyager, and it had recordings of nature sounds, sounds of the wind, sounds of surf, sounds of the birds, and recordings of greetings in 55 different human languages, and much more. And someone had built this beautiful installation of the golden record out there in deep playa. And one evening, there were these two women standing and looking at the installation, and out of the darkness, this guy, was it you? Oh, sorry, because she was waving. And out of the darkness, this guy cycles out of the darkness, looks at the installation, and he exclaims, "No way!" And he does a big loop, and he comes back, and he's completely astonished, and he rips open his shirt, and he's got a T-shirt with the golden record. And now these two women are thinking he's the artist who built the installation, and he's trying to explain to them that no, it was just sheer coincidence that he was some random guy wearing a T-shirt of the golden record, and some other random guy had built an installation of the golden record. So that's some playa magic there, playa synchronicity. So the golden record is still on board the Voyager 1, and in 2013, NASA announced that Voyager 1 had left the solar system. And it's the first man-made object to have left the solar system. Now, how do we know where the solar system ends? Well, the sun releases all these charged particles in the form of solar winds, and the farther away from the sun, the lower their energy. And when the outward pressure of the solar winds is in equilibrium with the inward pressure from the interstellar winds, we say that's the edge of the solar system. And that's at around 20 billion kilometers away. And so in 2013, NASA announced Voyager had left the solar system. So now if we are to explore the rest of the universe, we need a different measure of distance. Kilometers and miles won't cut it anymore, so we'll use a light year. Now the light year isn't a unit of time, it is a unit of distance. It is the amount of distance that the light covers in 1 year. So in 1 year, traveling at 300,000 kilometers per second, light covers 9.5 trillion kilometers, or 6 trillion miles. That's a huge amount of distance. So using that as a unit of measurement, how far to our next door neighboring star, Proxima Centauri? I'm sure some of you know. Anyone would like to call out? Yeah. 4.2 light years. Traveling at the speed of light, traveling at the speed of light, it would take you 4.2 years one way and another 4.2 years to return. But what if you were traveling on Voyager, one of the fastest man-made objects? Voyager is traveling at 20 kilometers per second. Traveling at that speed, it would take us over 60,000 years to get to our next door neighboring star, Proxima Centauri. So the question is, how many stars in our Milky Way galaxy? Well, before we get to that, let's imagine we can we have a clear night, it's an absolutely perfect night, and we're looking up in the night sky, we could see around 3,000 to 4,000 stars. And all those 3,000 stars would be in this little yellow circle. They're just a few thousand light years away from us. And if you're Star Trek fans, all the action that takes place in Star Trek, even when they're traveling at warp 9, is in just this tiny quadrant, or tiny part of the Milky Way galaxy. And that's just one galaxy. So, how many stars in our Milky Way galaxy? Those of you who know, you know. But those of you who don't, I'm sure you're tempted to say millions and billions and trillions. So before we answer this question, let's get a sense of how much a billion is. 1 billion is 1,000 million. And you can visualize it in the form of stacks of cash. Another way of visualizing it is to, or understanding it, is to ask ourselves, how long would it take us to count to a million and a billion? So if you counted one number per second, 1, 2, 3, it would take you 12 days to reach 1 million. But it would take you 32 years to count to 1 billion. In other words, if you started counting in 1990, you would reach 1 billion seconds about now. But what about a trillion? It would take you 32,000 years to count to a trillion. So these are some big numbers we're talking about. So how many stars in a Milky Way galaxy? There are roughly 300 billion stars in our Milky Way galaxy alone. So our Milky Way galaxy is part of what's called the Virgo cluster. This is a cluster of around 1,500 galaxies, and these are all fairly close to us. But the Virgo cluster is itself part of the Virgo supercluster, which has around 45,000 galaxies. So let's come back to our Milky Way galaxy and consider how far to our next door neighboring galaxy, Andromeda. Traveling at the speed of light, it would take us 2.5 million years to reach Andromeda. And in between, there is absolutely nothing. It's just the vacuum of intergalactic space. So now coming to the question, how many galaxies in the visible universe? Well, here's an image of the Hubble Deep Field on the left and the James Webb Deep Field. And what they did was they focused the Hubble telescope and the James Webb telescope on a tiny part of the night sky, an uninteresting part of the night sky. Didn't look like anything was happening there. And they allowed the light to filter in. And when they processed it, this is what they saw. Each point of light in this image is not a star. It's a galaxy with billions and billions of stars. And so if we are to ask ourselves how many galaxies in the universe, well, there's 2 trillion galaxies, each with on average 100 billion stars. And so there are more stars in the universe than there are grains of sand in all the deserts and beaches of our planet. So in this metaphor, our sun is just one grain of sand in all the deserts and beaches of our planet. So the universe is nearly 15 billion years old. It's over 90 billion light years across. And so there's a lot to explore, and we have amazing scientists working at CERN, working on optical telescopes and X-ray telescopes and infrared telescopes, and they're trying to figure out what's going on out there. And I'm sure now that you've listened to how vast and mysterious the universe is, the big question on your mind is, do aliens exist? And the honest answer is, the honest scientific answer is, we don't know. We don't know if aliens exist. But we can categorically say we don't have any hard evidence for aliens right now. And so that brings us to the Fermi paradox. Enrico Fermi was a mathematician, and he said, well, if the universe is so old and so vast and there are trillions of planets and galaxies, why is it so quiet? Where is all the intelligent forms of life? And so there are many responses to the Fermi paradox. One is to suggest that perhaps the more intelligent and advanced the species gets, the more likely it is to destroy itself. Another is to think like Neil deGrasse Tyson and say, we haven't explored enough yet. We've only started exploring the night sky for the last 50 years or so. And that's the equivalent of sitting in a boat, going to the middle of the Pacific Ocean, dipping your hand in and saying, oh, well, there are no whales in the Pacific. The point is, we haven't been looking long enough or far enough. So it could be that the universe is teeming with life, but we just haven't been looking long enough. But my favorite response to the Fermi paradox is called the transcension hypothesis. Perhaps some of you are aware of it, but this was put forward by futurist John Smart as a response to why we haven't encountered intelligent life forms. And he suggests that the more advanced a species gets, the less likely it is to explore outer space, and the more likely it is to explore inner space. So the more advanced we get, the more we're going to see compression in space-time energy matter. We're going to manipulate space-time at the femto level, the femto scale, and create black hole-like conditions and slingshot ourselves to the future and encounter all the other advanced civilizations out there. I know it sounds far out, it sounds like science fiction, that's why it's called a hypothesis. But it's a fascinating hypothesis. Another answer to the Fermi paradox is the dark forest hypothesis. I don't want to spend time explaining it, but if you're science fiction fans, I highly recommend the Three-Body Problem trilogy by Chinese author Cixin Liu. It won the Hugo Award, and it was a New York Times bestseller, and it's an absolutely mind-blowing exploration of why we might not have encountered intelligent life forms. So, moving on. This is Stephen Hawking, one of the laziest humans ever to live, just sat on a chair, did nothing else. No, I'm kidding. Stephen Hawking was a brilliant guy, but he said something that a lot of people disagreed with. He once said, human beings are mere chemical scum on the surface of an ordinary planet revolving around an average star in an ordinary part of an average galaxy. Now, and that sounds a bit depressing to hear, but perhaps David Deutsch's perspective might cheer you up. David Deutsch is another genius. He's a quantum physicist, quantum computing physicist at Oxford, and in his book, The Beginning of Infinity, he explains why he disagrees with Stephen Hawking. He says, imagine the whole universe, right? And this is just one galaxy, but imagine the whole universe, and you divided the whole universe into cubes the size of our solar system. So each cube is about 20 billion kilometers across, right? So you divide the universe into cubes, and the question he asks us to imagine is, what would a typical cube look like? What would an average place in the universe be like? And most of us would assume, oh, the average place in the universe would be blazing with stars and teeming with planets and supernovas and things, but that's not accurate. A typical cube, an average place in the universe, would be cold, dark, and empty. How cold? Just about 1 degree Kelvin. That's just a fraction of a degree above absolute zero. How dark? So dark that if a supernova explosion took place and you were looking in its direction, you could wait for your whole life and not see a glimmer. And how empty? Emptier than the best vacuums we can produce here on Earth. So in this cold, dark, empty universe, Earth exists and life exists. But life doesn't just exist. Life flourishes here on Earth. 100 million species have existed on planet Earth. So something really special is going on here on Earth. So we are not chemical scum. We exist. We are alive. And we are here at Burning Man. So something really special is going on in the universe on planet Earth with intelligent life. We're not just ordinary stuff that's out there in the universe. Something special is going on. Consciousness exists here on this planet, and that's really special. So now would be a good time to ask, what is the universe made of? all the stuff that you see, all the planets, galaxies, supernovas, and everything else, constitutes just 5% of what the universe is made of. So all this that you can see with your eye is called baryonic matter, and that's just 5% of the universe. 95% of the universe is called dark matter and dark energy. We know it's there because we can measure it, but we don't know what it's made of. So 95% of the universe is made of stuff that we don't know what it is. Another way of asking this question is to say, or to ask, what is reality made of? And a scientific reductionist way of answering this is to examine reality by zooming in. And you could zoom in all the way to the level of the elementary particle. So particles like electrons, quarks, photons are called elementary because if you split them up, you just get more of the same. So if you split an electron, you just get more electrons. If you split a photon, you just get more photons. If you split a quark, you get more quarks. So what is an elementary particle? It is essentially a pattern of energy. We used to think of elementary, but what is this pattern of energy? Another way of describing an electron would be to speak of it in terms of its properties. The only sensible thing, if you say what is an electron, all you can say about an electron is to talk about it in terms of its mass, its spin, and its charge. But what are these? It's pieces of information. So in one way, elementary particles are made of information. We used to think of particles as particles, but we now acknowledge particles are actually part of what's called a quantum field. Every elementary particle is part of what's called a quantum field, and a particle is an excitation in this field. So what is a field, a quantum field? It is a thing that has a value at every point in space. But then what is this thing? Again, we come to that word, information. So over and over again, if we ask ourselves, what is the universe made of? We come back to this word, information. You could zoom in still more, all the way down to the Planck scale. And here physicists tell us the universe or reality is made of quantum foam. What is quantum foam? It is essentially a fluctuation in space-time at a very, 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 very tiny scale. At this scale, matter and antimatter in the form of virtual particles pop in and out of existence. So the quantum foam or reality or space-time is this boiling, roiling, seething sea of particles and antiparticles popping in and out of existence. There's tremendous energy in there at that Planck scale, but we don't know how to harness it. And so when you bring it all down and ask the question, what is the universe made of? The universe is really made of nothing. You know, it's made of virtual particles popping in and out of existence, but not nothing, rather no thing. It could be that the universe at the fundamental level is not made of any noun, and that the universe is made of a verb. The universe just is. And when we start to use this kind of language, we're drifting off into philosophy, and it's fascinating that the Eastern philosophies, represented by Buddhism, Zen, and Vedanta, have said for the last 3,000 years that reality is made of no thing. And so I really believe that if we're going to get a grasp of what reality is all about, we have got to take a multidisciplinary approach to understanding it. We need empirical evidence, but we also need mystical insight. We need reason and emotion. We need rationality and instinct. We need technology and philosophy. And above all, we need science and spirituality. I'd like to share a wonderful quote by Michael Shermer, who's the editor of Skeptic magazine. He says, if we define spirit as the pattern of information of which we are made, our genes, proteins, memories, and personalities, then spirituality is the quest to know the place of our essence within the deep time of evolution and the deep space of the cosmos. So a lot of people, when they hear about how mysterious and vast the universe is, they ask, what is the purpose of it all? What is the meaning of life? What is the purpose of life? And in some ways, maybe that's a bit of a naive question, because that's presupposing that there is a purpose. Perhaps there is no purpose, and we make our purpose as we go along. And I'm also reminded of this Chinese saying, find meaning according to the context. So if we looked at it from a physics perspective, perhaps the purpose of life is to overcome entropy. And from a chemistry perspective, perhaps the purpose of life is to hydrogenate carbon atoms. This is what Sean Carroll, the physicist, suggests. And from a biology perspective, perhaps the purpose of life is for genes to perpetuate. And from a spiritual perspective, perhaps the purpose of life is to experience the numinous and the transcendental and acknowledge our deep interconnection with all of space and time. And from an aesthetic, poetic perspective, perhaps the purpose of life is to experience the sublime and the beauty that is all around us. And from an artistic perspective, perhaps the purpose of life is to explore, create, and invent. And finally, from a human perspective, perhaps the purpose of life is to love one another and acknowledge our deep interconnection with each other. I'd like to end my talk with a few salient quotes that resonate with this whole idea of the cosmic perspective. And here's Alan Watts, who says, "You are the universe experiencing itself." What does that mean? Well, Carl Sagan has this beautiful response. He says, "We are the representatives of the cosmos. We are an example of what hydrogen atoms can do given 15 billion years of cosmic evolution. At the Big Bang, there was just hydrogen, some helium and lithium, but mostly hydrogen. And 15 billion years later, here we are." And so that's what Alan Watts means when he says, we are the universe experiencing itself. And Lawrence Krauss says, stars died so that we could live. Another way of saying this is, we are stardust. This isn't poetry, it isn't metaphor, it is actual scientific fact. All the elements in your body, the iron in your blood, the calcium in your bones, the carbon and nitrogen in your organs, all these existed in the insides of stars that exploded when supernova and scattered their enriched guts out into the universe. So our sun is a third-generation star. And all the stuff in the planets and all the stuff that we are made of and everything around us came from the insides of stars that exploded. So we are literally stardust. Neil deGrasse Tyson, and what's more, there is a one-to-one correlation between what we are made of and what the universe is made of. The most abundant elements in the universe are hydrogen, helium, carbon, nitrogen, and oxygen. And what are we made of? There's a one-to-one correlation. We are also made of hydrogen, carbon, nitrogen, and oxygen. So we're not made of anything special. We're not made of some rare isotope or some rare element. We are made of the most abundant stuff in the universe. And that's why Neil deGrasse Tyson says, we are in the universe, and the universe is in us. And his latest book is called Starry Messenger, Cosmic Perspectives on Civilization. And here's a nice quote. He says, "Cosmic perspectives are ego checks on our self-importance. Messages from the stars forcing us to rethink our relationships to one another, to Earth, and to the cosmos. We may otherwise believe the world revolves around us and our opinions." Carl Sagan also said, "Astronomy is a humbling and character-building experience." So I'd like to hope that after you leave this talk, you start to see yourselves as cosmic citizens. Because in many ways, you are already global citizens. You have friends from around the world. Your sense of empathy extends to people of all races and all religions. And you are ready for something more. You're ready to be cosmic citizens and acknowledge your deep connection with the rest of space and the rest of time. A lot of people, when they hear about how vast and mysterious the universe is, they feel small. But I feel big. I feel I'm part of something far grander and greater and more mysterious than I can ever fully understand. The universe is only 15 billion years old. There are trillions and trillions and trillions of years left in the future. And so what I'd like to leave you with is this quote from the Imaginary Foundation, which says, think of an exciting, ecstatic, desirable future and pull the present forward to meet it. Thank you for listening. And if you have any questions, I'll be happy to take it on the side because we're run out of time. Thank you so much.